Hello everyone. Today we're going to look at implicit differentiation. Now we have two types of equations. We have an explicit equation, which is where y is isolated on one side of the equation and it equals to an expression that is completely in terms of x. And this would mean that it is clearly a function because you have only one y value for every x value. An implicit equation, however, is when it is not in terms of y, meaning that your equation is not y equals to something. It may be even impossible to solve for y. And typically, implicit equations are not functions, and that would mean that one y does not go or is not the result of one x value. So here we have these two equations. The first one here is an explicit function, which we know how to find the derivative of this because we've done this before, right? So if I were to rewrite this as y is equal to 25 minus x squared raised to the 1/2, I can find the derivative by applying the chain rule. So y prime would equal to 1/2 times 25 minus x squared, x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. Here the 2 and the 1/2 would cancel, and my derivative would equal to x over the square root of 25 minus x squared. Now, this equation, however, is an implicit function, and that's because we see here x squared plus y squared is equal to 25. This equation is not written in terms of y, and if you were to try to solve for y, you would get two equations. You would get y is equal to plus or minus the square root of 25 minus x squared. I mean, I did that pretty quickly, but basically if you subtract the x squared and square root, you would get the plus or minus. So this is considered an implicit function because y equals to two separate equations. So when we're finding the derivative of an implicit function, every time you find the derivative of y, you multiply it by dy dx, which means the derivative of y with respect to x. So let's go ahead and work this out, and of course I'll break it down later, but just so you can get an idea, you find the derivative as normal. So we would go 2x plus 2y, and then here we would multiply dy dx, and it equals to 0 because the derivative of any constant is 0. When you do this, then your goal is to solve for dy dx because that's the equivalent of y prime. So we want to get that alone so that way I have the derivative of y with respect to x. So we would subtract this 2x and we get 2y dy dx is equal to negative 2x. Finally, we would divide the 2y. And here we would get my derivative dy dx is equal to, these 2's would cancel, so negative x over y. Typically, implicit functions, when you get the derivative will have both x and y as part of your derivative answer. And so if you're trying to find the derivative of an implicit function at a particular point, you would need both the x and the y value in order to find that derivative. So now we're going to have a look at how this process works a little bit closer. So here we have the equation of a circle. Now, just so you understand where this equation comes from, the equation of a circle is this: x minus h squared plus y minus k squared is equal to the radius squared, where h and k is the center of the circle. So in this equation, we have the center of the circle is at 3, 2, which you can see is on the graph. And the radius, since this represents the radius squared, the radius is 5. And we can see that if we just count, we have 1, 2, 3, 4, 5, and so 5 squared is 25. So just in case if you were wondering where that equation comes from for this particular circle. Now what we're going to do here is we're going to differentiate this implicit function. All equations of circles are considered implicit functions. These are the steps when you are finding the derivative of an implicit function. You would first differentiate both sides of the equation with respect to x. Then you would collect all like terms involving dy dx on the left side of the equation and move all the other terms to the right side of the equation. If you have multiple terms on the left side that include dy dx, then you would factor the dy dx out of that, and you would solve for dy dx by dividing both sides of the equation by the left-hand factor that does not contain dy dx. And that's how you would go about differentiating implicitly. So let's try that out with this particular function, or rather equation. When we find the derivative of this circle, this is chain rule because we have a binomial within parentheses and the exponent. So we can go ahead and start that off with 2x minus 3 times the derivative of the inside, which is just 1, plus 2y minus 2 times the derivative of the inside, which even though the derivative of y is 1, remember that because the derivative of y, we would multiply by dy dx, which is equal to the derivative of 25, so 0. Now I want to isolate dy dx, so I'm going to subtract this 2x minus 3 over to the other side. So what I have here is 2y minus 2 dy dx is equal to negative 2x minus 3. And now to get the dy dx alone, we would divide by 2y minus 2. When you do that, the 2's here would cancel out. And so we get our final derivative answer as dy dx is equal to negative x minus 3 over y minus 2. Now we're ready to fill out this chart here. We have these particular coordinates and we want to know what the derivative is at these coordinates. Remember that when we're finding the derivative value for an implicit function, we need both the x and the y, which is why we're given those coordinates. So let's try that out. We're going to plug in x is equal to negative 1, so that would be negative 1 minus 3 is negative 4 over 5 minus 2, which is 3. And this gives me a positive 4 over 3. Now, what does this value tell us about the graph? This means that our function, or I keep saying function, but you know what I mean, the equation, right? The equation of the circle. At that point in time, at the coordinate negative 1, 5, the graph will be increasing because we have a positive derivative value. And if you look here at negative 1, 5, you can see that if you were to read your graph from left to right, that particular part is increasing. At 3, 7, if you plug in 3, you would get 3 minus 3 in the numerator, which is 0, over 7 minus 2 in the denominator. So 0 over 5 is just equal to 0. And this means that at that particular point, we have a horizontal tangent, which is also where we have any extrema. So if I go to 3, 7, which is right here, this is the maximum of my graph. So we would have that horizontal tangent. Next, let's try 6, 6. If you plug in 6 into the numerator, you would get 6 minus 3, which is a positive 3, but then this negative, making it a negative 3, over 6 minus 2, which is 4. So we end up with a negative derivative value. This means the graph will be decreasing. And again, if you look at the graph at 6, 6, you can see that our circle is going down at that point, so it is decreasing. For 8, 2, we end up with a numerator of 8 minus 3, which is 5, and then with this negative, so negative 5, over 2 minus 2, which is 0. Now, because here we have an undefined value, on the graph, if you go to 8, 2, which is right here, this would be a vertical tangent. So if you ever have an undefined derivative value, it is very possible that it is most likely because we have a vertical tangent line there. Let's try this with a couple of other problems, and we're just going to now find the derivative. We have y squared is equal to 2x plus 3y. So remember, when we're finding the derivative, we find it like normal. So the derivative of y squared will be 2y, but then we always multiply by dy dx is equal to 2 plus the derivative of 3y, which is 3, and then we multiply dy dx. Our second step here is going to be to move all of the values with dy dx over to the left side of the equation. So I'm going to subtract this 3 dy dx over. So now my equation would read 2y dy dx minus 3 dy dx is equal to 2. Once you have all of your dy dx's on the left, what you would do is factor out the dy dx. And when you factor it out, we're left with 2y minus 3, which is equal to 2. And our final step now to solve for dy dx would be to divide by 2y minus 3. So our derivative answer, dy dx, is equal to 2 over 2y minus 3. Let's go ahead and try another one. We have 2x plus e to the y is equal to x squared minus y squared. When we find the derivative, we get 2 plus e to the y times dy dx is equal to 2x minus 2y dy dx. Again, I want to move all of my dy dx's to the left and everything else to the right. So I am going to add this 2y dy dx. And then I'm going to subtract this 2, since it does not contain dy dx. So now this is what I have. E to the y dy dx plus 2y dy dx is equal to 2x minus 2. We're going to factor the dy dx out, and we're left with e to the y plus 2y is equal to 2x minus 2. And finally, we divide e to the y plus 2y, and that is our derivative. So dy dx is equal to 2x minus 2 over e to the y plus 2y. Let's try a couple more before we move on. We have here 2xy is equal to 3y squared plus 2x. Now x and y, we're going to consider that as like two separate functions. So here we're going to have to use the product rule. Since they are two different variables and we're finding the derivative with respect to x, we need to remember that this is going to be a product. So that means that the derivative of 2xy would be the derivative of 2x, so 2, leave y alone, plus now you leave 2x alone, times the derivative of y, which is 1, but then we multiply dy dx. And that's going to equal to 6y dy dx plus 2. Just like in the previous problems, we're going to go ahead and move all of my dy dx's over to the left and everything else over to the right. Now, I keep saying that we're going to move the dy dx to the left, but it does not necessarily matter whether you choose to move it to the left or to the right, as long as all of the dy dx's are on the same side of the equation. I just always move to the left because I like what I'm solving for to be on the left side. But again, it does not matter. So here I'm going to go ahead and subtract this 2y to this side. And then I'm going to subtract this 6y dy dx over to the other side. So now what I have is 2x dy dx minus 6y dy dx is equal to 2 minus 2y. And now I'm going to go ahead and factor that dy dx, which would leave me with 2x minus 6y is equal to 2 minus 2y. And finally, we divide the 2x minus 6y. Which leaves me with my derivative dy dx is equal to 2 minus 2y over 2x minus 6y. Now, additionally, this is the answer. But if we wanted to, like let's say if this was a multiple choice question and you're positive that this is your answer, but you don't see it, it's probably because it could be simplified. All of these coefficients can all be divided by 2. So we can rewrite this as 1 minus y is over x minus 3y. And this would be another option for the derivative answer. Let's do one more. We have 5x cubed plus 3 is equal to 2y minus 3x squared y. So again, when I scan this, I notice that I have this product. So you have to remember that you're going to have to apply the product rule for the 3x squared y since there are two different variables. So now when we find this derivative, we have 15x squared. Derivative of 3 is 0, so equals 2 dy dx minus, now I'm going to apply the product rule. But when I apply the product rule, notice that this is minus, meaning that we're going to subtract the derivative of the product. So I would have to open a parenthesis so I don't forget that I'm going to have to distribute that negative after I apply the product rule. So the derivative of 3x squared would be 6x, and we leave y alone, plus now we leave 3x squared alone, and times the derivative of y, which is dy dx. I can now distribute this negative, so 15x squared is equal to 2 dy dx minus 6xy minus 3x squared dy dx. See, now here typically I move my dy dx's over to the left, but all of the dy dx terms are already on the right. So instead, I'm just going to add this 6xy over to the right, to the left. And then already all of my dy dx's are isolated on the right side of my equation. So we have 15x squared plus 6xy is equal to 2 dy dx minus 3x squared dy dx. Again, we can factor the dy dx, and that's going to leave me with 2 minus 3x squared. And so our final step would be to divide the 2 minus 3x squared. So that means that dy dx is equal to 15x squared plus 6xy over 2 minus 3x squared. Now, just as a side note, this is my answer, but depending on where you move the dy dx terms will determine your signs. So the numbers will always stay the same, but let's say if I had moved all my dy dx's to the left and everything else to the right, then an equivalent answer would be negative 15x squared minus 6xy over negative 2 plus 3x squared. So both of these mean the same thing, as long as every single term switches signs. So that's just in case if you have a multiple choice question and you see your answer, but all of the signs are different, that just means that dy dx was solved for on a different side of the equation, but it would still be correct. Now we're going to look at a couple more analytical questions. We have here, for what values of x will the curve x cubed plus y cubed is equal to 4xy plus 1 have a horizontal tangent? So for this particular question, we are going to use the graphing calculator. Now, before I whip out the calculator, when we are finding the derivative of an implicit function, that we have to do by hand. Okay, and we'll get to the rest on the calculator in a moment. Now, in order to figure out when a function or when this equation is going to have a horizontal tangent, remember that that is when the derivative is equal to 0. So what we're looking for here is when dy dx is equal to 0, and we want to solve for x. So first, let's find the derivative, remembering that this here is a product. So we have 3x squared plus 3y squared dy dx is equal to 4x, the derivative of 4x is 4, and then times y, plus 4x times the derivative of y, which is dy dx, plus the derivative of 1, which is 0. I'm going to subtract the 4x over, and I'm going to subtract this 3x squared. So what I have now is 3y squared minus 4x dy dx. And what I've done here is that I already know I'm going to end up factoring the dy dx. So I just wrote what I had, which was a 3y squared minus 4x. And already it's already factored. So that's a little shortcut you can take if you'd like. If not, no problem. Which is equal to 4y minus 3x squared. So now we would divide this, and we get that dy dx is equal to 4y minus 3x squared over 3y squared minus 4x. Now, from my derivative to equal to 0, this means that only the numerator needs to equal to 0. As long as the numerator equals to 0, it does not matter what the denominator is equal to. So what we do is we make the numerator 4y minus 3x squared equal to 0. Now, I can't exactly plug this into the calculator because we have y and x squared as part of my equation. So what we can do is solve for y. So I would add 3x squared over to the other side. And so we have 4y is equal to 3x squared, and then divide by 4. So we get that y is equal to 3x squared over 4. So this right here, this equation for y, represents when my function or when my curve is going to have a horizontal tangent. But what I have to do here is that I know what the y is equal to, so we need to plug this back into the original function so we can figure out those x values. I can't just figure out when this equals to 0 because, yes, that would give me when the derivative is 0. We want to know what value of x will the actual curve equal to 0, will have a horizontal tangent. So we take the equation x cubed plus y cubed, and instead of y cubed, I'm going to put 3x squared over 4 cubed is equal to 4x times y, which is 3x squared over 4, plus 1. And now what I want to do is I want to solve for x. Now, I don't want to solve for x because this is very complicated, and it's a good thing that this one is a calculator question. So all I have to do now, remember that the calculator cannot solve for an equation, cannot solve for a value of x for any particular y. So you have to make this equation equal to 0. So what I would do is simplify this a little bit so that way we are able to plug this into the calculator without too much difficulty. So we have x cubed plus, now I'm going to actually cube this. 3 cubed is 27, x to the 6 over 4 cubed, which is 64, is equal to 4 times 3, so 12, x cubed over 4. Oh, I could have just canceled out these 4's, huh? Well, we'll do that now. And then this will be 3x cubed instead, plus 1. So now I'm going to make this equal to 0. And I get the equation negative 2x cubed plus 27 over 64 x to the 6 minus 1 is equal to 0. And now I'm going to go ahead and put this into the calculator. So it was, I'm going to go to my y equals screen. Oh, I'm going to check my window. Okay. Negative 2x to the third plus, I'm going to open parentheses for my fraction, 27 over 64, close, x raised to the 6 minus 1. And now I'm going to go ahead and graph. Now you see here that we have 2 x-intercepts. So that means that we are going to have 2 answers, and we're going to find both. So we'll go to second calc. Remember that we go to 0. Select the left bound. I'm finding the left x-intercept first, and the right bound. And I get that x is equal to negative 0.7697. So that's one solution. Negative 0.7697. And now we're going to go ahead and find the other solution. So I'll go ahead and go to second calc again, option 2. Now I'm looking at the right x-intercept, so I'm going to go to the left of that x-intercept, and then to the right. And we get 1.7321. So these would be my 2 x's that would give me a horizontal tangent of 0. Let's look at the next question. In terms of y, describe the values of x for which the curve x cubed plus y cubed is equal to 4xy plus 1 will have a vertical tangent. Now this is the exact same function as this previous example here. So we have a vertical tangent when the derivative is undefined. And because the derivative of implicit functions is typically a fraction, the derivative will be undefined when the denominator is equal to 0. So we're going to take that denominator, 3y squared minus 4x, and make it equal to 0. And now since it says, in terms of y, describe the values of x, that means that we are going to solve for x. Whenever you see that wording in terms of y, that means that the answer will have y in it. So we're going to solve for x. So we would subtract this 3y squared. And we have negative 4x is equal to negative 3y squared. And then divide the negative 4. So x is equal to positive 3y squared over 4. Now this means that the curve will have a vertical tangent when x is equal to 3y squared over 4. That's what that means. Now we're going to look at one more thing. We're going to look at the second derivative for implicit functions. This is the notation for the second derivative. So if you ever see this notation, d squared y over dx squared, that means to find the second derivative of the implicit function, or of any function. That notation just means to find the second derivative. So we need to find the first derivative before I can do that. So that would be 2y dy dx plus 2 dy dx is equal to 2. So far, so good. Now that dy dx is already all on the left side and there's nothing else there, I can factor it out. And we get 2y plus 2 is equal to 2. And then we can divide that 2y plus 2, which can be simplified because all of these coefficients can be divided by 2 to 1 over y plus 1. So this is my dy dx. To find the second derivative would be the derivative of dy dx. So now we're going to have to, you can either apply the quotient rule if you like, right? Because this is technically a quotient. Or what we can do here is rewrite dy dx as y plus 1 raised to the negative 1. So what I did here is that I made this into its own factor and moved it up to the numerator. Since the numerator is just a constant, which is 1, it's just getting multiplied to that number. So now when we're finding the second derivative, that's d squared y over dx squared, we can apply the chain rule. So we have negative 1 y plus 1 raised to the negative 2 times the derivative of the inside, which is dy dx. Now, because the second derivative has this part here, which is dy dx, we have dy dx. So what we can do now is substitute the dy dx with the 1 over y plus 1. So I'm going to start this again. We have negative 1 y plus 1 raised to the negative 2 times 1 over y plus 1. Now the algebra here could be done many different ways. You can rewrite this and multiply and that whole bit. That would actually work. Or you can bring this up and then multiply add the exponents because it is the same factor. There's lots of ways that you can work this out. So what I'm going to do here is that this is the negative, because the negative 1. That y plus 1 raised to the negative 2 is the same thing as 1 over y plus 1 squared, and then times 1 over y plus 1. Because these are the same factors, we just add those exponents. So this is equal to negative 1, because now it's just in the numerator, over y plus 1 raised to the third power. And this would be my second derivative. Let's try that one more time. Given the curve x squared plus y squared is equal to 1, find the second derivative. So let's go and find the first derivative, which is 2x plus 2y dy dx is equal to 0. We're going to subtract the 2x over to the other side. So 2y dy dx is equal to negative 2x, and then divide the 2y. So we get that dy dx is equal to negative x over y, since those 2's there cancel out. So now we're ready to find the second derivative. Here I cannot apply that chain rule because in the numerator it's not just a constant, we have another variable. So if you move it up, then it would be y to the negative 1, and you can apply the product rule, or we can just apply the quotient rule, which is what I'm going to do. So for the quotient rule, remember that we bring the denominator up times the derivative of the numerator minus, now we leave the numerator alone, times the derivative of the denominator, which is dy dx, over the denominator squared. So anytime you see that dy dx, we're going to substitute it now with the negative x over y. So this is equal to negative y plus x times negative x over y all over y squared. Now for the numerator, remember this is a complex fraction and we don't like leaving our answers as complex fractions. So we're going to rewrite this so that it's no longer a complex fraction. All I've done so far while I was just talking was I multiplied the x times the negative x, which gives me a negative x squared over y. So here what we need is we need a common denominator so I can write the numerator as just one fraction. So if I put this over 1, the common denominator here would be y. So I would multiply y here and y here, which would then give me negative y squared minus x squared, and since now they both have the same denominator, it's over y. And everything is over y squared. Because this is still a complex fraction and we are dividing, remember to copy, change, flip. So negative y squared minus x squared over y times 1 over y squared. And this would give me a final derivative answer for the second derivative, d squared y dx squared, would equal to negative y squared minus x squared over y to the third. And this is our implicit derivatives.